Morning, everybody. So you may already have noticed that I graded your midterms. And you can take a look at your midterm paper after the class today at 1:30. I also decided on your programming assignment. I'm going to announce it today, but I'm also going to give you some kind of a template code, in which you are going to also, if you know OpenGL, you can also do that very easily, but for those who do not know OpenGL, it's going to, I'm going to provide you a code for you to visualize your results, okay? And the problem is going to be this. Let me you may wonder what the programming assignment is going to be. It's going to be, you are going to be given, right now you cannot probably, you are going to find it difficult to find a solution for this problem right now, but it's going to be related to what we are going to see today. And also a hint, this is a hint, so it's going to be related to what we are going to see today and what we have seen a couple of weeks ago. So we are going to use both techniques. And the question is this: we are given two sets of points in the plane, on the plane. So there are black points and there are red points, or objects you can call them. And your goal is to find out whether there exists a line that separates, let's put black here, whether there exists a line that separates these 2 point sets. Okay, so you are going to be searching for a line. Any line would be fine. You're just going to say whether such a line exists or not. If you find that line, you are going to give the line equation. All you are going to do is just write a function which outputs a line if there exists a line. And it takes as parameter 2 sets of points. And that your function is going to find out whether such a line exists or not. If it exists, it's going to output, it's going to return this line. And yes, this 2D. The points are going to be two-dimensional, okay? And actually a linear time solution exists for this, okay? The number of points. In the number of points, you can find this line out of all the infinitely many lines. You can, the search space is infinite, but a linear solution in ON time. And actually expected linear time, let me tell you, and this is another hint. In expected linear time, you can find a solution to this. But you're free to find other solutions. I'm not going to ask you to find the expected linear time solution. If you can find another solution, that's fine. You're free to implement any solutions that you find. But you are going to see that after what we see today, the problem can be solved much easier than the original problem. So what we are going to see today is arrangements and duality. So the dual of this problem, I'm giving lots of hints today. So the dual of this problem is going to be much easier to solve. Okay, so let's start with duality and arrangements today. And this is chapter 8 in your textbook. And first I'm going to describe the motivating problem, the application area of the focus of this chapter, which is supersampling in ray tracing. So ray tracing is a technique in computer graphics to generate images of three-dimensional scenes. But we are not going to, we are going to turn this problem in ray tracing to a completely geometrical problem, a different problem. The ray tracing also is a geometrical problem, but we are going to take only a sub-problem in ray tracing, which is supersampling. Maybe you haven't heard supersampling in ray tracing. And our goal will be to find random sampling, to determine whether random sampling of a point, some set of points is a good sampling or not. Okay, so this is the main problem. So I'm going to first describe that. So let's start with ray tracing. So what do we do in ray tracing? So the goal of computer graphics is to generate 2D imagery for three-dimensional virtual scenes. So what we have is that we have a three-dimensional virtual scene, okay? And we look at this scene through a camera. And the camera, there's an image plane actually, okay? And there's a focal point of this image plane. And this image plane is composed of discrete, and when we are talking about images, what we have is something discrete, okay, with a certain resolution. So this is our image with a certain resolution, and our goal is to generate which of these three-dimensional objects contributes to the color of a certain pixel in this 2D image. So that's the main thing in computer graphics. We want to determine which object, which three-dimensional object in our scene contributes to this pixel. There are different techniques to generate this image, and in ray tracing, what we do is we shoot rays from this focal point, which pass through each of these pixels to find out which object this ray hits. And the other, actually, this is not the only power of ray tracing. The other power of ray tracing is that by following this ray, by following the intersections through the other objects, we can find out the contribution of other objects' intensities on this pixel location, for example. So we can find some, for example, light that is reflected, so we can find reflections on other objects on certain objects. So the power of ray tracing is about reflections. But the goal is it can intersect many objects. It can intersect another object behind it. So this line, this half line that we shoot from this point may intersect many objects, and the first object that is intersected is going to be the one that is going to contribute to this pixel. Okay, so but the problem we are going to be dealing with is not about intersections or the general ray tracing algorithm. So sometimes what happens is that, as you can see, when we are shooting this ray, this pixel actually has a certain width and height, right? The actual pixel is not a point. But when we are generating this half line, we need to select a point in order to have a unique half line that is defined. This is a focal point. It has to pass through another point in this image plane. So we select a point on this pixel, like the center of this pixel can be chosen to form this line, right? But as you can see, depending on the resolution of your image, these points are going to be, there is going to be some distance between them. They're not, you cannot, you can increase your resolution, of course, but there's another technique to generate a better. So what happens is that instead of, for example, why did we choose the center pixel? Not the center point of the pixel. We could have chosen the upper left corner, upper right corner, one of the four corners, or we could choose an arbitrary point inside this pixel, right? Here, one thing that we need to also find out is that because of the image resolution, sometimes when an object, so now let's forget about this picture, now let's look at a single pixel, okay? In a single pixel, if just zoom in that single pixel, an edge of a polygon in the 3D scene may, for example, intersect only a small portion of this pixel. And when we shoot a ray here that passed through this point, we are going to say that we didn't hit this object. Our ray is not going to hit this object because this object only occupies partially, this pixel is only partially occupied by this pixel. We are not going to be able to detect this partial occupation of this polygon. So based on our resolution, we are going to have jagged, we are going to have a certain pattern among it's not going to be smooth. The polygon edges are not going to appear smooth. So one solution we can do is we can increase our resolution. Okay, that's one obvious solution. If you're not very happy with the picture you get, if you can see those zigzags, one thing you can do is just increase your resolution. And one solution to increase this resolution is to divide your pixels into regular grids and shoot from the centers of. So this amounts to increasing the resolution. Okay. For example, how many I have drawn here? 30. So I increased the resolution 30 times more. Okay, so if the image I was generating was, if it was 1 megabytes, now I'm generating an image 30 megabytes. Okay, now as you can see, what we have here in this regular grid is that 3 of the new sample, so this is called super sampling. It was actually for a single pixel. You can choose many points within the pixel to, you shoot many rays. Instead of shooting a single ray from the single pixel, shoot many rays that go through the same pixel. So, this is like not thinking in terms of increasing resolution. We are going to still have the same resolution. We can, one thing we can do is, we can still have a 1 megabyte image. At the end, the image we generate can be 1 megabyte. The image resolution is the same. But based on the amount of this pixel occupied by the object, if we could determine, if we could say that this polygon occupies 30% of this pixel, this polygon occupies 50%, this polygon 80%, we could maybe use different shades of color for, we are to have like a, which is going to, it's like anti-aliasing. You can have a smooth, the polygon edges may appear smooth if we could determine for each pixel, what is the percentage of that pixel which is occupied by the polygonal object. Okay, the final image that we generated is going to still have this many pixels, but each pixel is going to have a different shade, different intensity based on how much it is hit by the polygon phase. And the way to do the way to compute this percentage. What is the percentage of this polygon? What we do is we do super sampling. Instead of shooting a single ray, because in single ray, you just, if your object appears to intersect at the center of this pixel, you can find that it's hit. So if you just have one point, it's a binary decision. It's either hit or miss. Okay, so you either have a black color for this pixel or a white color. Okay, if your polygon was black, it's either black or white. But can we have the other shades of green by determining the percentage of this polygon? And we can do that with the help of super sampling. Instead of shooting a single ray, shoot many rays through the same pixel. These rays can be arranged regularly like this. And to determine the percentage of the area occupied by the polygon. So our goal is to find, measure what is the percentage of this triangle to the pixel area. If we can find it accurately, we can paint it with the correct intensity. Now, however, now I'm going to provide, so everybody understand what super sampling is, right? So this is super sampling in ray tracing. This is going to be the main application that of today's computational geometric problem. Another alternative would be, instead of having this regular points, we could randomly, given a pixel like this, we could randomly sample in this pixel, right? Instead of a regular super sampling, we could randomly super sample this. And if your goal is just to find the percentage of this area, what the book says is that human vision, these regular supersampling, if there is an error in this, if there is an error in this computation, the regularities in errors can be seen very easily by human vision. Okay, if there's some regularity, if we can detect patterns, certain patterns. Even in this version, we could still see some zigzags, some jagged lines along the. Even in this version, this regular sampling may have some problems. If there's an error, if we cannot compute this 100% accurately, imagine instead of dividing it with 30 cells, you divided it with 4 cells, you could still have some regularities. So this regular subdivision, its main disadvantages, if there's some error in this regular, in what you compute, human vision is going to catch that regularity in the image that you generate. So it's better to, instead of a regular supersampling, if you did it randomly, okay, for each pixel, if you just generated a random set of points, you supersample it randomly like this, you generated random set of points within this pixel, and you shoot these rays through these points. The human vision is going to less likely, since each sample is different between pixel to pixel, we are not going to detect it as, even the polygon edge is not appearing smooth, we are going to perceive it as a property of the object itself. It's maybe not a smooth object, but it's not going to be a regular thing. So it's going to look more natural. So that's the main motivation behind random supersampling. Okay, now this is the application motivation, and then this turns out the problem that we are going to solve is that given two random supersampling of points, which one is a better sample? Which one is a better random sample? What does it mean better? Okay, now imagine there's a polygon that intersects the pixel like this, and throughout our discussion, throughout this chapter, we are going to assume that each pixel is intersected by at most one polygon, okay, one polygon edge. Because we are talking about a pixel here, okay, two edges intersecting the same pixel. It can happen if you have many polygons in the scene, many objects in the scene. This is possible, but we are not going to consider this problem, okay. We are going to assume that our pixel is intersected by one polygon edge, and here our goal is, remember, the purpose of the sampling is to find the percentage of the area of the polygon occupied by this polygon with respect to this pixel. We are going to name this the continuous measure, okay? Which is, if you could compute, if this line is given to you directly, if this line that passes through this pixel, and if you know these coordinates, and if your pixel is from 0 to 1, okay, 0 to 1, its area is unit area, its area is 1. You can compute the area here by just computing the areas of these two triangles and summing them up. And the area of this triangles, these two triangles, the summation of these summation of this area over, this ratio, the actual area over 1 is going to give us the actual percentage that we're trying to find. Okay, this is the percentage that we are trying to find. But the thing is, we don't know these intersection points. We don't know where our polygon intersects with this pixel. In ray tracing, we don't do that. What we do is we shoot rays and we just check whether this ray hits the object or not. Now, instead of this, we try to approximate this measure by a discrete measure, which is the number of points that are inside this one over the total number of points that you have sampled. Okay, so this is what we call is the discrete measure. So the percentage of points, the that are below this. It's going to be a half plane here if you consider this. This polygon is going to determine like a half plane, and we are interested in the half plane that is inside this pixel. And the number of points in this half plane divided by the total number of points in this pixel is going to give you an approximation of the area of the polygon of the actual continuous measure. Okay? Yes. Oh, okay. It's just arbitrary. I mean, just if your polygon is like this, okay, if your object is like this is going to be the part that is intersected. If your object was something like that, we could take the no, actually, these are solid objects. Okay, they're faces. Okay, so that's a good question. So if any part is unclear, please ask. This is important to understand this part of the problem, because we are going to tackle this problem next. So what we have is faces of we are going to assume most of the computer graphics scenery is composed of polyhedra. Okay, they are closed polyhedral objects. So what we are going to have faces. Which probably most of the time are composed of triangle. So we are going to have triangular meshes in our scene, and a triangular mesh, an edge of this face is going to intersect this, and one part of this edge is going to be the face. Okay, so it's one part of this edge is going to determine where the face is, and the other is not the face. So depending on either it's this side or this side. But our goal is to find out how much of this face is intersected by this pixel.
Çizgi de aslında olabilirdi ama piksel seviyesini düşününce aslında çizgi de face oluyor. Hani
yeah, maybe. I mean, even in, I mean, no. If it's a line, your line probably maybe appear like a strip here in pixel. So we are not talking about pure lines in the scene. So in our scene we have polygons. So but this is a good question. What we are computing here, the difference in these ratios, which is called discrepancy, can be computed differently from a class of objects to another class of objects. If you were trying to solve this problem for lines, for example, if you had lines in your then you would consider the width of that line, and you are going to find the points within this width of line. So, or maybe if you had some circular objects, I mean not lines, maybe your polygons may not have edges, you may have some splines there, for example, then you would have a different way to compute these hits. It depends, what we are computing here depends on how the scene is composed. And in this problem, we assume that our scene is composed with polyhedral objects. Okay, so what we have is polygons. So a polygon edge intersects a pixel, and the polygon face lies to one side of this line, this edge. Okay, so this is what we have, and our goal is how much of this polygon face is visible within this pixel. If we knew these intersection points, we could directly compute this percentage, but we cannot. This is much difficult. I mean, to finding the intersection points on the image side. I mean, we need to shoot rays from infinitely many points here to the images. I mean, it's reverse ray tracing. But the important thing in ray tracing is that we have a finite number of pixels, so it's better to shoot from pixels to the objects. And here we are in continuous space. Our virtual scene is continuous, so you cannot shoot from every part. I mean, to find which this is an edge like this. To find these intersection points, we need to find the intersection of each point along this edge with the pixels, which is very difficult. So how much you are going to sample? So this is a much difficult problem. So we are not. So we know. You can assume that we cannot find these intersection points directly. So what we need to do is, to solve this problem, to solve the percentage of this area, what we do is we do approximation. Since we cannot compute this continuous measure, we approximate it by a discrete measure. We just sample a number of points within this pixel. We shoot rays through these points and count how many of these rays hit the object. And the percentage of the rays that hit the objects are actually the number of points that are below this half plane in this pixel. So now, given a line, if this polygon was given a specific polygon, we can compute this. And given a specific polygon, we can compute, if we know the specific polygon, so given a specific polygon, we can compute the percentage by looking at this ratio, how many points are below with respect to the total number of points. Okay. Now, for a specific polygon, we can compute this ratio. Now, let's get back to the original problem. Whether a certain sampling of these points, let's get back to this problem. For example, look at this sample, these 4 points, they are there, and look at another pixel in which the 4 points are like this, okay? I mean, obviously, this, each of them uses 4 points to supersample, but obviously, I mean, by intuition, you can see that the right one is a better supersampling because the points are more dispersed, and in the other, the points are clustered here. What will happen is that, for example, for an object, for a polygon, which intersects our pixel like this, we are going to say that the polygon is fully intersected by the pixel because all 4 points, again, if this part is the polygon face, all 4 sample points is below this line. So we are going to say that we are going to think that this polygon is fully contained here. However, actually, it's like only maybe 30%, something like that. So this difference between the continuous measure and the discrete measure. So here, discrete measure says it's 1, okay, 1/1. So it's 4/4. This is what discrete measure says. 4/4 points. This is the percentage. 100% the polygon is contained in. But the actual measure is what? The actual measure is like maybe 30%. Actually, the 30% of this polygon is inside this pixel. So this difference, which is like going to be 0.7, is called the discrepancy between the continuous and discrete measure. So this is our error. So this discrepancy is our error in this sampling. Now, we computed this discrepancy for a specific polygon. Now the question is this: in order to compare, right now we don't have a specific polygon. We are just comparing two different samples. Which sample is better than the other? So we are not given a specific polygon edge. So how are we going to compare them? What we are going to do is, out of all possible polygon edges, what can the maximum discrepancy be in these sample points? Okay, so this is, I mean, it took like half an hour to get the final computational geometry problem we are going to solve, but this is what we are going to solve. So given a set of points, our goal will be, what is the maximum discrepancy? I mean, can we draw a certain half plane? Can we draw a certain line segment within this pixel, which is going to maximize this measure? For example, I told you that it was like this. So it was like this, and it was 0.7, right? Now, if you do it if you lower this a little bit more, what happens is that the discrete measure stays the same. So there are still 4 points under it, but the area under is even smaller. Okay, so what happens is that you increase the discrepancy, right? So there can be, so the maximum discrepancy here, for example, maybe but we don't know. I mean, maybe this one is even smaller. I mean, this is 0.75, but the area you exclude here may be larger than the difference between 0.75 and 0. I mean, it doesn't seem like that in this example, but when we are computing this discrepancy, we are not always going to have all 4 points under the line. Sometimes half of the points may be under the line, and the difference may be huge. Okay, so out of all possible lines through here, okay, which line is going to give you the maximum difference between the actual area and the number of points below it? Okay, so this is the maximum discrepancy of this point set we are. And this maximum number is going to be like what is the worst case performance of this random sample set? Okay, what is the worst case performance of this random sample? And by comparing the worst case performances of two different sample sets, we can say one of them is better than the other. Okay. Now, so this problem, so this is the problem we are going to solve, right? Everybody understood this problem? Given a point set, what is the maximum discrepancy of this point set? So out of all possible half planes that we can draw, or you can say line segments we can draw within this pixel, what is the maximum discrepancy that we are going to obtain? And obviously the search space here is infinite. You have infinitely many, you can draw infinitely many lines here. But here, what we observed, imagine, get back to this example of these two parallel lines. One of them was 0.7, okay, so let me erase this one as well. Just look at these. Okay, look at these two. So when I check this arbitrary line here, I found that the one I can translate this line until I hit a point, and this translation is going to decrease the continuous measure. The area is going to decrease, while the number of points under it remain the same. And this is going to go on. I mean, so it means that I don't need to check, actually, I don't need to look at any point. I mean, all these here are going to have a smaller discrepancy than the red line here, which is actually hitting a point. Now, so there's a way actually to reduce this infinite search space to a finite search space. So is it possible to select a set of lines here in which we guarantee the maximum is going to be obtained in one of them? So, I mean, can we reduce the infinite search space to a finite one? Is there? Maybe, yeah, convexal, it may be a good idea to consider the convexal. But still, it's not, lines can pass in between the points as well. So the half of, we are not going to, our goal is not going to have all of the points under it. So there may be a line in which half of the points is above, half of the points is below, but this discrepancy may be maximum at that point. Okay, so this is, convexal is not going to help in that regard. But what we are going to observe is that, I mean, this observation at least tells us that this point, this line that we drove should pass through a point here, okay? So since we have finite number of points, but now the question is it going to, can I also, for example, look at this point here? If I rotate this line, so is it going to, are there going to be 2 points on this line or a single point? So can lines with single points on them can achieve a maximum discrepancy, or can I continue decreasing it until I hit 2 points? Okay, so this is, so the goal, the reason I'm doing this analysis is I'm trying to find out whether I can decrease this infinite search space to a finite number of lines. So can I continue decreasing? So can I have a set of lines in which they're the local extremums in themselves. They are the local extremum points. And by inspecting all these local extremums, you can find the global extremum, global maximizing point. So can we find this one is going to be the next thing we need to analyze. And the thing is, we can actually have a local extremum on a line that passes through a single point. It's like this. Even if you rotate and if it doesn't hit anything, it's possible. So this is a point, and there's a line that passes through it. So by rotating this line around this point, and there may be other points here, when we rotate this line around this point that it passes through, the discrete measure is going to change. Some of the points is going to be under, some of it's going to be. So when we're rotating it, the discrete point is also continuously, it's not continuously changing, but at intersection points with these, some of the points may go above it, some of the points may go below it, and the area is also continuously changing as we, so when you rotate this line, the area under this line is also changing. But the book has a formula indicating this area that is under here. When it's changing, it's not continuously increasing or decreasing. So it has some maximum points, it decreases as it reaches another maximum. So there is a certain landscape that, there are a number of extremum points based on which, so here it's intersecting the left and right edge of this pixel. During this intersection, it's going to, when it's come to corners, it's going to start increasing again maybe. So at these different intersection points, for example, it can intersect these two, or these two. So there can be 4 different cases, I guess. So we can compute in the book, the book says that there are 4 extremum points when we rotate this line around it. The area under it is going to reach 4 local maximum points. Okay, so it is possible to reach a maximum. So a line that passes through a single point can give us some maximum discrepancy. So we need to consider all the lines. So there are n such lines. If we have n points in our sample, we can draw n such lines that pass through these points. We are going to rotate all of them. Since we can use the formula in O1 time, we can find out for each of these lines what is the maximum area or minimum area under them. But for each line, it's going to take, for a given line, what is the time complexity of determining which points are above, which points are under it? It's ON, right? So you need to check each point. The discrete measure is going to be more difficult to compute. The continuous measure, you can formulate it. You can find the formula, since this is a unit square here, 0101. You can formulate, given a line that is passing through a point, you can formulate the maximum area that the area under this is going to obtain by using a formula. So in O1 time, you can compute the maximum or minimum continuous measure. But in order to compute the discrete measure in these maximum points, you need to check each point, whether it's below or above it. Okay, so it's going to take ON time to compute a discrete measure. How many points are below it? How many points are above it? So we need to check each of these n points. And since there are n such lines, we are going to look at all these lines that pass through all these points, single points. The lines that pass through single points, there are n such lines. Actually, we are rotating each of these lines, but we are not doing this rotation 360 degrees. I mean, we just compute this using this formula for this continuous, the area continuous measure can be computed in O1 time. And the total running time is going to be O(n) square. So for n of these lines, we can compute the maximum discrepancy for n of these lines. And at the end, we are going to, in O(n) square total time, we are going to find out which one of these lines can have the maximum discrepancy. Okay, this could solve the problem if these were the only points in our infinite search space. These were the only possible lines. Unfortunately, there are also lines that pass through 2 points. Okay, so in our finite search space, we need to also consider lines that pass through 2 points. And unfortunately, the number of such lines, okay, I mean, you may ask that, okay, why didn't we see this line when we were rotating it around it? We didn't see this line because we are not doing the rotation on n points. When we have a line that passed through these points, we only consider its intersection with the corner points when we consider these continuous measure. We don't consider the combinatorial intersection with the other lines. Okay, so that's why we could do it in O1 time. Now, so we need to also consider lines that pass through 2 points. So for every pair of points, generate a line. There's a unique line now. There's no rotation now. Okay, there's no rotation now. For each pair of lines, for each pair of points, we have a line that passed through them, and there are n square such lines. In actually n times n minus 1 divided by 2. Such lines, and for each of these lines, determine how the area, the continuous measure, and how many points are below it, how many points are above it. Okay, so n square lines, each one takes O(n) time, so we can find a solution in O(n) cube time, right? So now the technique that we are going to see is going to reduce this to O(n) square. Okay, so for O(n) square, different lines, we are going to be able to compute how many points are below them, how many points are above them for every one of them in total O(n) square time. So this seems like impossible, right? So it's like there are n square such lines. It means, I mean, you should spend O(n) time for each of them in order to guarantee this. I mean, in order to find how many points are above them, how many points are below them. But we are going to be able to do it in O(n) square time total by transforming the problem to a different plane. Okay, we are going to see duality after the break. So before we start talking about this solution, let's have a break, and then we are going to